Hey everybody, this is video lesson 1 on chapter 10, Kinetics. The first thing we're going to talk about are the factors of things that make reactions go. Kinetics is all about speed. We're talking about how fast can we get a chemical reaction to go. Some reactions go fast, some reactions go slow, and some reactions fall in between those two on the continuum of speed. Now there's a handful of things that we can do to help make chemical reactions go faster. And then there are really 4 things that I want to talk about on this first slide. We'll list the 4 things, and then over the course of the next video lessons, we will talk about the finer workings of these 4 things. The first thing we're going to talk about is how concentration plays a role in determining the speed of a chemical reaction. Concentration, specifically molarity, is one of the most important things to discuss when describing the kinetics of a reaction. The next 2, heat and agitation, will be discussed kind of together. We'll discuss how those 2, heating up a solution, or heating up a chemical reaction, I should say, and agitating, like stirring or shaking, can help make a reaction go faster. We're going to kind of bubble these together and call them physical factors. And then finally, the 4th thing we're going to talk about is how you can make a chemical reaction go faster using catalysts. The first thing we need to do when discussing reaction rates is really be able to define what you're really measuring. The rate of what, and then specifically, what are the units of that rate measurement? Now in physics, rate is like distance covered per second, but in chemistry, we measure the rate in two different ways, based on how much molarity changes over a period of time, or how much pressure changes over a period of time. Concentration is used for solution chemical reactions, like aqueous solutions, for example, whereas pressure changes are most used when the chemical reactions are in a gas phase. So the first one, change in concentration over change in time, is used for aqueous solutions or aqueous chemical reactions. And the other one, pressure over change in time, is used for gas phase chemical reactions. But it's worth pointing out that we're not only going to use change in pressure versus time for gases. In fact, as we learned about in the gas laws chapter, that the concentration and the pressure are directly related using ideal gas laws. So sometimes we'll refer to chemical reactions in gas phase in terms of molarity versus time. But just know that these 2 are proportional to one another, especially when discussing gas phase. So the units for an aqueous chemical reaction is molarity per second, usually, could be molarity per minute, but usually molarity per second, whereas for pressure, it's atmospheres of change per second. Now, if you're a calculus student, and most of you are, this notation right here should jump off the page at you, because this is basically dx over dt, and that's really what we're doing. We're going to be looking at curves change over time, and we're going to sprinkle in a little bit of derivatives. Now, I personally am not too well rehearsed on the concept of derivatives and integrals. In fact, you don't need to know calculus in order to be able to teach this class. You don't even need calculus in order to take this class. But the fact that a lot of you have a background in calculus actually puts you at a pretty good advantage. Hopefully you'll be able to connect the 2 concepts here as we move forward. Now, on a half joking, half serious note, it would be appreciated if you just not challenge me with your calculus-like questions, because honestly, you're smarter than me at calculus, and we all know that, so let's just get that out of the way right now. And I appreciate all of your restraint here in advance. Let's take, for example, the chemical reaction A plus B gives you product C. Now, if I'm going to talk about the rate of this reaction, I can reference each of these substances to describe the rate. Rates for a reaction can be expressed based on how quickly the reactants disappear and how quickly the products appear. Take, for example, once again, my general form of a chemical reaction. So A is going to be disappearing. So A, the concentration of A goes down over a certain period of time, and that's the same as the concentration of B, since these are in a 1-to-1 stoichiometric ratio. And we're going to talk about how stoichiometry plays a role in a rate of reaction here in the not too distant future. But first, let's just kind of start with the basics. So A disappears over time. The same is with B. B disappears over time, which is why the sign out in front of those are negative. Or we could express the rate of the reaction by how much the concentration of C appears over time. In fact, all of these would be equivalent, and we could describe the reaction in reference to any one, or in respect to either of the reactants or the product. Here's an example of a reaction across the top of this graph. We've got a reactant with water producing two different products. And this is a curve that represents the concentration, in fact, of that original reactant over time. So what we're doing is we're graphing the disappearance of one of the reactants as time goes up. This table over here on the right kind of gives you a play-by-play. After every 50 seconds, it tells you what the concentration is at that time. So it's worth noting that at the fastest this reaction will ever be going is at its instantaneous time zero rate. And as the reactants react, you have less and less of the two reactants, and the reaction slows down gradually, eventually flatlining off into no reaction happening any longer. And the reason a reaction slows down as time progresses is because if you think about each of the reactants have to be physically touching in order for the reaction to occur, the less reactant that you have as time progresses, the less likely those two reactants will come in contact with one another. So the speed is dependent on the concentration. As the concentration goes down, the rate in which the reaction occurs slows down. You can see that by this graph over here on the right. In the first 50 seconds of this reaction, the speed is measured in a 1.9 times 10 to the negative fourth molarity change per second over those 50 seconds. And then the next 50-second interval, it slows down a little bit, and then a little bit more, and a little bit more. And every 50 seconds, if you monitor the rate of the reaction, it gets slower and slower and slower. Now, we measure the rate as an average rate. And as you can see on this graph, if you draw a tangent line to the slope, you can get a straight line, and the slope of that line is going to equal the rate of the reaction at that particular point in time. So the slope of a tangent line is equal to the rate in molarity per second. And in this case, we're looking at the change in the molarity, how much is decreasing over a particular time period. Now I'm going to lean on you calculus folks again, but basically what you're looking at is a derivative. A derivative is defined as a tangent line to a slope. So if you knew the equation of this line, this decay, you can figure out its derivative. You can basically determine the slope of the line and thus the rate. But in order to do that, you need an equation of the line, and we don't have that. So we do this graphically. We look at the experimental data, and we determine just kind of what the slope of the line is at time zero. Or we could look at 600 seconds, the slope of the line, so we just kind of draw it in. And I guess the point I'm trying to show right now is that it's steepest at zero, but the line gets less slopey. The slope of the line, tangent to the curve, gets less steep as the chemical reaction progresses. For any particular point on this graph over a certain time period, you can calculate the average rate by simply taking the change in rise versus run, the old school version of calculating slope. So if we let it run for every 50 seconds, then you go from 0 to 50 and you calculate what the change in concentration is. It looks like it goes down by 0.01 molar. So if you calculate that out, you could figure out the average rate over the first 50 seconds. So you don't necessarily need a derivative to do this. You just look at the graph and calculate it the way you were taught in algebra. And when I do that, I get negative 0.0002, or pretty darn close to what I got here, 1.9 times 10 to the negative fourth over the first 50 seconds. So my calculated versus the actual table falls pretty good. So I can be pretty confident that I can use rise over run to determine the average rate if you were given a graph like this. Now, as I talked about a few slides back, stoichiometry plays a role in determining reaction rates. And everything's nice and easy if your reaction is everything in a 1-to-1 ratio. But if it's not in a 1-to-1 ratio, you need to factor in the stoichiometric coefficients in order to determine the reaction rates. And so any general reaction moving forward we're going to use the form A moles of A plus B moles of B gives you C moles of C plus D moles of D, where the lowercase letters are your stoichiometric coefficients and the capital letters are your reactants or your products. And if everything's in a 1-to-1 ratio, then everything is just determined to be, the concentration of A over change in time and how it decreases. But when we factor in the stoichiometric coefficients, we slide the molar coefficient in the denominator. It's how much concentration of A goes down divided by the stoichiometric coefficient times the time. And as you'd probably expect, if you take a look at each reactant, you can express the rate of the reaction as any of the reactants or any of the products, just now factoring in the stoichiometric coefficients in the denominators of each of the rates. So you can use that relationship I just described on the last slide to be able to apply it to an actual chemical reaction. In this case, we know the rate of the decomposition of the reactant, and we're asked to figure out what the rate of appearance of both the products are in this particular instance at this moment in time. So if I write out the rates of each of the reactants and products with respect to one another, you get the concentration of the reactant disappearing over 2 times the delta T. That's equal to the rate of NO2 appearing over 4 delta T. As you can see, the stoichiometric coefficient is in the denominator. And since this is a stoichiometric coefficient of just 1, it's just the rate of appearance of O2 over change in time. So this question asks for the rate of appearance of each of your products. So if I stick 4.2 times 10 to the negative second in for this concentration over 2 delta T, and I set that equal, and I'm going to do the first one here, this is what it looks like. If I call X the concentration of NO2, then I'll put that up here in the numerator of this one that I'm setting equal to the other one. And since it has a stoichiometric coefficient of 4, that goes in the denominator. And you simply just solve for X. And so I multiply both sides by 4 to get rid of the 4. Multiply by 4. 4 reduces to the 2 to 1. And so you got 2 times negative 4.2 times 10 to the negative second molarity per second. Now the negative sign here doesn't necessarily factor into the math because this just simply tells us that this is a reactant disappearing. The question asks what is the rate of appearance, so X is going to be a positive number. Now mathematically, if I multiply both sides by -1, or just solve for X in this case, I'm going to have a negative number, but I don't really factor that in because we know that this is negative because it's disappearing and this is positive because it's appearing. So if I do the math quick, X is equal to 2 times 4.2 times 10 to the negative second, or 8.4 times 2 to the negative second molarity per second. That's X. So the rate of reaction with respect to the product is double that based on the stoichiometric coefficient. And that should make sense to you because when you look at the stoichiometric coefficients, you create 4 of these for every 2 of these you lose. So the rate of this appearing should be twice that of the rate of disappearance. And I just cleaned up that number on the bottom so it looked a little better. So that equals the rate of appearance of the NO2 over change in time. But I need to calculate the same for O2. So I'm going to do the same thing as I did before. I'm going to do 4.2 times 10 to the negative second molarity per second over 2 is equal to Y, and I'm going to call Y the concentration change per time of oxygen over 1 second because the stoichiometric coefficient of the O2 is just 1. So this is easy, you just solve for Y. So when you take 4.2 times 10 to the negative second and divide by 2, Y should equal 2.1 times 10 to the negative second molarity per second. And again, that should make sense stoichiometrically. It should be half as much because when you look at the stoichiometric coefficients, if you go for every 2 of these, you only create 1 of these. So the rate of this disappearing should be twice of that than the rate of appearing of this. Or this O2 should be half as fast because you're only creating half as much. Well, that takes care of this first video lesson on the introduction to kinetics. The next video lesson is going to cover something called rate laws, which is a mathematical relationship that describes how a chemical reaction occurs and then the speed at which it does occur. So stay tuned for that. Thanks for listening.